Okay, so thank you for the introduction, and thank you very much to the organizers. It's always a great pleasure to be back in Vienna. So what I'm going to talk about today is based on joint work with Oude Groeniger and Oliver Petersen, and it's about, well, quiescent singularities. So it's about Big Bang singularities. So initially, I suppose Einstein wasn't very fond of the idea that there were singularities in the solutions to his equations, and it took a while before people accepted sort of that singularities appear quite naturally in general relativity. And the sort of turning point, I suppose, came in the mid-60s, right? Because, well, it was both the observation of the cosmic microwave background radiation, but from a mathematical point of view, it was the singularity theorem by Hawking. I've sort of phrased the theorem here. The details are perhaps not so important, but the idea of these singularity theorems is that you have some rather general geometric conditions that give you the conclusion that there is an incomplete time-like geodesic. That's sort of the structure of these types of results. And the details of the assumptions are perhaps not so important at this point, but what is important is that they're sort of robust. I mean, if you have sort of a solution satisfying this, you perturb the initial data, then you sort of get the condition is still satisfied. So this is an indication that the occurrence of singularities is sort of not due to a high degree of symmetry of the solutions or anything like that. It's something that occurs naturally in general relativity. So that's the assumptions. What about the conclusions? So the conclusions is here that there is an incomplete time-like geodesic. So what does that mean? So in general relativity, freely falling test particles follow time-like geodesics. So that there is an incomplete time-like geodesic means that you're sort of reaching the boundary of space-time in finite proper time. So something is going wrong, right? And if you ask Hawking and Penrose, they will tell you that's a singularity, right? But that's a little bit debatable because these theorems, they don't say much about the nature of the singularity. I mean, you would like, if it's a Big Bang singularity, you would like to be able to say that, well, actually the gravitational fields blow up, right? I mean, this is the sort of thing you would like to claim if there is a singularity. This is not a conclusion that you get out of these singularity theorems. So there are lots of questions that remain unanswered, right? So it would be very nice to have a theorem with general conditions giving the existence of a Big Bang singularity with curvature blow-up, right? And that's sort of what I'm aiming for today. That's the sort of purpose of this talk today. So that's sort of perhaps the main motivation. And I mean, this is then, of course, also related to the strong cosmic censorship conjecture. Can you predict what space-time you're in on the basis of initial data and so on? That's perhaps not going to be the focus of this talk. But okay, so this is a mixed audience. So I'm gonna start from sort of the standard perspective and of cosmology and sort of build from there somehow, right? So let me now start at the sort of the starting point. If you would ask a cosmologist or a physicist, the universe is spatially homogeneous and isotropic, right? So this is for them the starting point. And well, we saw the metrics 2 days ago in 2 of the talks. And currently, physicists actually prefer spatially flat space-times. That's the current preference, right? So the only freedom you have left then in the geometry, as we saw 2 days ago, is one scalar function of time. That's the only freedom that's left in the geometry. There is nothing more, right? Okay? And so what about the matter content? Well, so usually you have ordinary matter, which is modeled by dust. And also you have dark matter, also modeled by dust, or you can model it by dust. Then you have radiation, modeled by radiation fluid. And then also, typically these days, people include a positive cosmological constant to sort of explain the accelerated expansion at late times, right? But if you're now going, and in the early universe, you can also have inflation. We'll get back a bit to inflation later, but I mean, it's not going to be the main, perhaps. I'm not going to talk about it right now. So, but anyway, if you now go towards the singularity, then, I mean, the only freedom that you have left for the matter content is really, I mean, if you've decided on an equation of state, the only freedom you have left is actually the energy density, because due to the symmetries, the fluid velocity has to be perpendicular to the hypersurfaces of spatial homogeneity. So the only freedom left for fluid is the energy density, right? And then you can see how does the energy density scale for these different types of matter models. And then you see that actually the radiation fluid, it's going to scale like a to the -4 or something like that, right? So, and this is going to dominate over all the other sort of matter contributions. So when you go towards the singularity, people would typically just throw out everything else. The cosmological constant is irrelevant. The dust is relevant. You have the Einstein radiation fluid. That's the relevant sort of equations to look at if you want to sort of analyze the singularity. Okay. And so now you can ask a basic question. If you have a spatially flat, isotropic solution to Einstein's equations coupled to radiation fluid, is this stable now as you go towards the singularity? It's like a basic question you can ask, right? Okay, now if you want to ask this question, you of course have to pose it in a somewhat more general context than spatial homogeneity and isotropy. And the easiest way to generalize this setting is to allow for anisotropies. We can still insist now on spatial homogeneity and spatial flatness, but let's admit some anisotropy in this game, in the geometry. And so I need to introduce now some sort of terminology for the anisotropies, and this I'm actually going to do in a completely general setting. It's going to apply to this particular setting, but I want to do it in general, right? So let me introduce sort of a terminology for the anisotropies. Okay, so the object to have in mind here is that, okay, so you have a space-time, so manifold M with a Lorentz metric G, and let's say it has a foliation. Let's say it's just a Cartesian product like this, so M bar cross I. And the constant T hypersurfaces, they are now space-like Cauchy hypersurfaces. So what does that mean? So the induced metric is Riemannian, that's space-like. And that it's a Cauchy hypersurface means that it's intersected exactly once by every inextendable time-like curve. So this simply means that Cauchy hypersurfaces, these are the right type of surfaces on which to put initial data for the wave equation. Okay, so that's what that is. And then the sort of crushing singularity means that the mean curvatures of these leaves blow up uniformly in the direction of the singularity, right? So that's what it means that it's crushing. And so what's the mean curvature? Well, this is just a trace of the second fundamental form. And so in my convention that theta, the mean curvature is positive, means that the volume element is increasing, right? I mean, that's what that is. Okay, good. Now, a fundamental object in this talk will be what I call the expansion normalized Weingarten map. And it's defined as follows. So let's assume that we have a hypersurface, the mean curvature is positive, and then I will not look at the second fundamental form, I will rather look at the Weingarten map. So this is just the second fundamental form with one index raised. So it's a 1-1 tensor field. So it's like an operator on the tangent spaces of the leaves of the foliation, right? That's what that is. And now we know the trace of this object, the trace is the mean curvature, and I mean, by assumption, this is blowing up, right? So we know if we want to extract meaningful information as we go towards the singularity, we need to somehow normalize this in some way. And one naive way to do that is just to divide by the trace. We just divide by the mean curvature and then sort of hope that this is going to be meaningful. And this object will be completely central throughout the entire talk somehow, this object. It's a very simple object, but it's very important. Okay, and now isotropy is effectively sort of captured by this script k being a multiple of the identity. Or more specifically, it's going to be 1 over the spatial dimension times the identity, right? That's isotropy. Okay, so deviations from that is anisotropy then somehow. And another important observation here is that, okay, so this script k, it's symmetric with respect to the induced Riemannian metric on the leaves of these foliations. So this means that you're going to have n real eigenvalues. I'm going to denote them LA. And by the normalization, they're going to sum up to 1, right? And so in 3+1 dimensions, we have 3 eigenvalues. They sum up to 1, so 2 functions is enough, right? So it's convenient to, you can introduce these objects, for instance. So L plus and L minus. This contains equivalent information to all the eigenvalues of the expansion normalized Weingarten map. And with this terminology, the origin corresponds to isotropy. So yeah, L plus and L minus equals 0, both of them, that's the isotropic situation. And then I'm also going to talk about sort of quiescent singularities. I'm going to be a lot more specific in a moment what I mean by quiescent singularity, but at the sort of minimum requirement is that these eigenvalues are converging as you go towards the singularity. and oscillatory is not quiescent. I'm going to be a lot more specific about this in a moment. Okay, so now we can actually return to this question. What was the basic question? Are these spatially homogeneous and spatially homogeneous, isotropic, and spatially flat solutions to the Einstein radiation fluid equations, right, which is a nice model as you go towards the singularity? Are they stable now as you go towards the singularity? Okay, so then you have this picture. So this is the state space if you insist still on spatial homogeneity and spatial flatness, but you allow anisotropy. So here you have the L plus L minus. This is sort of measuring the anisotropy. And then you have omega, which is an expansion normalized version of the energy density, right? And so these are the sort of 3 degrees of freedom here. But due to Einstein's equations, there is a constraint. So you're constrained to be on the half sphere. So you have to be on the half sphere here. And the isotropic solution in this expansion normalized perspective is just one point. It's one fixed point, the North Pole F here. And if you perturb this thing, then what happens as you go towards the singularity? Well, the arrows here indicate the dynamics as you go towards the singularity. Actually, you move away from F, and you move down here to the base of this half sphere. So you move to this circle. The circle is representing vacuum solutions, so spatially homogeneous and spatially flat vacuum solutions to Einstein's equations. These are the Kästner solutions, and this is called the Kästner circle, and you move down there. So clearly, this isotropic solution is unstable, right, in the direction of the singularity. So this is clearly unstable, okay? On the other hand, I mean, it looks nice here that the circle is stable in this perspective, right? On the other hand, now you can ask the question, what happens if I actually turn on spatial curvature? So let's see, what happens if I turn on spatial curvature? Well, then this is what happens. So now I'm looking at the L plus L minus plane. I've sort of suppressed the matter dimension. It doesn't matter anymore. And say now that you start here on the Kästner circle, so you start at this point S, and now you perturb it, you admit some spatial curvature. What's going to happen then? Well, then this point is unstable, and you're going to move like this. So more specifically, you take the closest corner of the triangle, you draw a straight line to S, and then you continue until you intersect this circle again. So this defines a map from the unit circle to itself called kappa, so the Kästner map or BKL map, if you will. And of course, once you get over here, this is also unstable, so you move out over here and so on and so forth, right? And now, the interesting thing, so this circle with the map kappa, it's a one-dimensional dynamical system, and this one-dimensional dynamical system is chaotic, right? So this is a chaotic dynamical system. And it gets worse. So the thing is that the idea here is that this is what happens for each spatial point, so to speak. You go towards the singularity, each observer will experience its own little chaotic dynamical system, right? So you have, infinitely many chaotic dynamical systems going towards the singularity. So this is sort of the picture you have. So it's a mess. That doesn't look very promising. Prove something. Of course, it would be very nice to be able to prove something about this. There are results in the spatially homogeneous setting. Those were pretty hard to come by. And even in the spatially homogeneous setting, where it's just a system of ODEs, the picture is still not complete, right? So it's still rather complicated. Okay, but is there some situation which is a little bit easier? Well, if you look at the case of the Einstein-scalar field equations, or the Einstein stiff fluid equations, you get the same pictures here. So again, energy density and isotropy. But in this case, the entire half sphere consists of fixed points. So a stiff fluid is where the pressure is equal to the energy density, right? So then all of it is fixed points. So what happens now if you admit some spatial curvature? What's going to happen to these fixed points? Well, many of them will disappear, but some of them will remain. So inside this triangle, actually, these points still stay stable, right? So if you have the Einstein scale field equations or Einstein's fluid equations, even if you do sort of allow spatial curvature, this regime is still stable, right? And I mean, in practice, you can have a combination of these things, right? I mean, you could have, okay, you start out close to this thing, Einstein radiation fluid, you move down to the base here, to the Kästner circle, you start bouncing around, perhaps for a long time, according to this chaotic dynamical system. But then at some point, the scalar field is going to set in and become important, and you're going to somehow move up in the energy density direction, and you're going to end up inside this triangle, and then you're going to settle down, right? So I mean, these types of dynamics are perfectly sort of possible in this setting. Okay, so this is, I mean, in some sense, ideas of this type, this goes back to the work of Belinsky, Kalatnikov, and Lifshitz. So these were Soviet physicists, right? So they were writing papers from the early 60s to the early 80s about this. And the idea is really that, well, in general, in 3+1 dimensions, for lots of matter models, in particular vacuum, you should get this chaotic dynamics as you go towards the singularity. So the eigenvalues of the expansion normalized Weingart map should sort of evolve according to this chaotic dynamical system. But then there are some exceptions, and then for particular matter models, so like a scalar field or as the fluid, then you can get, the eigenvalues can converge and you can get this quiescent behavior. Right? Okay, and either by heuristic arguments or, I mean, you can also do, if you make some rough assumptions about solutions and then try to figure out what is the consistency requirement to get this quiescent behavior, then it turns out there's a condition on the eigenvalue. So now I'm ordering the eigenvalue. So L1, so recall that LA, these are the eigenvalues of the expansion normalized Weingart map. Let's order them. So L1 is less than equal to L2, less than equal to L3, and so on. And then what you expect to be a necessary condition to get this quiescent behavior is that this condition is verified. So now we have two conditions on these eigenvalues. They have to sum up to 1. We have to have this condition. And then also, as you go towards the singularity, there is a third condition that has to be satisfied, and this is associated with the expansion normalized Hamiltonian constraint. So Einstein's equations imply a condition on initial data, which is called the Hamiltonian constraint, and if you sort of expansion normalize that and take the limit, you get a third condition. So for instance, in vacuum, you get this condition. So in vacuum, you have to have the LAs have to sum up to 1, the LA squares have to sum up to 1, and then you have to have this condition. And then you can ask yourself the question, are these conditions consistent? And it turns out that in 10 space-time dimensions and below, it's not consistent. In 11 space-time dimensions and above, it is consistent, right? So you can have this quiescent behavior in 11 space-time dimensions and vacuum, right? And also above. And I should say also this condition, in 3+1 dimensions, it corresponds to just the smallest eigenvalue being strictly positive, and it corresponds to being inside this triangle that I drew earlier, right? Okay. So here, you sort of expect oscillations if it's the space-time dimension is 10 or below. But if you have a scalar field, what happens then is that this asymptotic Hamiltonian constraint gets a contribution from the matter. And this contribution from the matter makes it possible to have this condition, this quiescence condition can be satisfied in any space-time dimension. In particular, it can also be satisfied in 3+1 dimensions. Okay. So, and this talk is focused on the quiescent situation, that you have this type of situation. So this is what Liam was talking about on Tuesday. Right? So, okay, so here the matter model I'm actually going to study is the Einstein non-linear scalar field system. So first we have the Einstein equation, so G equals T. G is the Einstein tensor, so the Ricci tensor minus a half times the scalar curvature times the metric. And in order to specify the matter model associated with a scalar field, all you have to specify is a potential. So V is a potential. It's a smooth function of the real numbers. But once you specify the smooth function, the stress energy tensor looks like this, and you plug that into Einstein's equations. And then, of course, there's an equation for the matter, which is this. So this is the Einstein non-linear scalar field system. This is the system of equations I'm interested in. And okay, so why am I interested in this potential and so on? Well, I mean, you can use this potential to model this inflation. And also, I mean, so since the late 90s, it's sort of clear that, I mean, the observations indicate that our universe is accelerating at expanding at an accelerated rate, right? And one way to sort of ensure that acceleration is by having a system like this. So there are actually quite a lot of results concerning, so future global nonlinear stability results concerning the system, right? So you already have, you know, understanding to the future. So now it would be nice to have understanding to the past, right? So then you would get stability results all the way from the Big Bang all the way to the future, right? Okay. Okay, so far I've been fairly vague concerning what is meant by quiescence, right? And now I'm going to go in the extreme opposite direction, and I'm going to be extremely specific what I mean by quiescence. And what's the most specific you can be about the asymptotic behavior of solutions to an equation? Well, if the asymptotic data determine uniquely the solution, you can't ask for a lot more information than that, right? So I'm going to introduce here a notion of data on the singularity, right? So, okay, so what are data on the singularity? So it's a manifold sigma, a Riemannian metric, script H ring, and then a 1-1 tensor field, script K ring, and then two functions, phi 0 ring, phi 1 ring. They're going to be smooth in this discussion. They have to satisfy certain conditions. The trace of this has to be 1. The script K ring has to be symmetric with respect to H ring. And there are these equations which are, in some sense, limits, expansion normalized limits of the Hamiltonian momentum constraint. And finally, there's this condition which I sort of indicated was necessary to get quiescent behavior, right? You can define the notion of data on the singularity even if this condition is violated. It is possible. Then you have to impose other conditions, and it somehow becomes non-generic. And I don't want to discuss that in this talk, so I'm sticking to this condition here. So this is a notion of data on the singularity. This notion is not very interesting unless I tell you how this notion is related to actual solutions. So what's the relation between these objects and an actual solution? Okay, yes? Right, no, they don't. So yeah, they don't. I mean, it simplifies some things, but yeah, here they don't. I mean, actually, okay, that sort of survived from the more general condition where you express things. But here, no, they don't. No, I mean that's. I'm actually gonna. Okay, but they don't have to be. That's true. It's a good point. Okay, so what's the relation now between an actual solution and these data on the singularity? So let's just imagine that we have a solution with a crushing singularity. So I have a space-time, I have this foliation of the space-time, and the mean curvatures of the leaves of the foliation are blowing up, right? So the mean curvatures are blowing up. And I want to describe what happens as the mean curvatures are blowing up. What are the asymptotics here? That's what I want to describe, okay? And one way to do that is to look for each leaf of the foliation. I can look at the induced initial data, right? So you should imagine I here as being initial data induced on a leaf of the foliation. For the Einstein's nonlinear scalar field equations, what are sort of regular initial data on a hypersurface? Well, okay, sigma is then sort of, well, the topology here of this hypersurface. Then H bar is just the induced Riemannian metric. K bar is the induced second fundamental form. Phi 0 bar is just the induced scalar field. Phi 1 bar, this is, if you take the future directed unit normal, apply it to the scalar field and restrict it to the hypersurface, then you get phi 1 bar, right? So this is just, you know, initial data. And And then I'm going to assume I'm interested in this situation that I have a crushing singularity, so the mean curvature is blowing up uniformly. In particular, I'm going to assume that the mean curvature of the leaves of this foliation is strictly positive. Okay. So now, I mean, I know already, so the volume associated with h bar is going to go to 0. I mean, you would expect. The mean curvature is blowing up, right? The scalar field is blowing up. The normal derivative of the scalar field is blowing up. So this information is not the right one to look at. I somehow have to expansion normalize these objects in order to extract the meaningful limit, right? And so then the question is, how do you want to expansion normalize this? So our suggestion is to do this, right? So, okay, so first, this script k bar, well, this is just the expansion normalized Weingarten map, just like before. So this is nothing strange. You take the Weingarten map, you divide by the mean curvature. A little bit more interesting, or perhaps the most interesting object here is this one. So as you're going now towards the singularity, the point is that the behavior is anisotropic, right? So the behavior is anisotropic. So you have contraction, but you have contraction at different rates in different directions. And I mean, more generally, you can have a situation where you have even expansion in the direction of the singularity for some directions, right? So if you want to get some meaningful limit here from the metric, you really have to compensate for this anisotropy, right? You have to compensate for this anisotropy somehow. On the other hand, the expansion normalized Weingarten map, so the expansion normalized Weingarten map is telling you in which directions do you have this different contractions and expansion. And it's also telling you the speed with which you're expanding and contracting, right? And theta bar, the mean curvature, is telling you in some sense the amount that you have expanded or contracted. So for that reason, it's quite natural to look at this theta bar raised to script k bar. Okay, this requires perhaps some explanation. So script k bar is a tensor field, so I'm raising a function to a tensor field here. But you remember that the script k bar, it's a 1-1 tensor field, so it's an operator on the tangent spaces of the leaves of the foliation. So what you can do to define this is just e raised to log theta bar times script k bar. And then you take the standard power series expansion for the exponential map, and this object makes perfect sense, right? This is a perfectly nice, smooth object, right? So there's nothing strange about this object, right? And then you also, I mean, since the scalar field is going to infinity and so on and so forth, you have to expansion normalize the scalar field. This is a little bit less strange. I mean, it's sort of rather clear in a sense. If you look at the equations and solutions, you see that this is sort of a nice, good thing to do. Well, it's the musical isomorphism. I mean, okay, I think Oliver is responsible for this, and I've taken it over. I mean, so k of x comma dot is a one form, and then you can raise an index to get a vector field, and sharp is just the operation, you know, taking a one form to a vector field determined by the metric h bar, right? So I mean, there's nothing deep there at all. So given these regular initial data, you get these expansion normalized data, and you have some hope that these objects might actually converge in the direction of the singularity. So remember, I mean, I don't only have one set of initial data here. We're looking at a crushing singularity. So I have a whole foliation, and for each leaf of the foliation, I get this expansion normalized data. And then the idea is that so I have a family of expansion normalized data, a family of script k bar, and they are then going to converge to the corresponding data on the singularity. The script h bar is going to converge to the corresponding data on the singularity, and so on and so forth, right? Okay. So this is okay. So this is somehow what you could hope for the asymptotics in the direction of the singularity, right? And this would be sort of an ideal situation where this can potentially also uniquely determine the solution. Okay. Right. So this is rather abstract. So it's of interest to apply this idea in a specific case for a specific family of solutions. So let's look at now spatially homogeneous and spatially flat setting. So then the solutions to the Einstein-scalar field equations, so the solutions to the Einstein-scalar field equations can essentially be written, they can be written like this, right? So this is the metric, and this is a scalar field. So the pi's, A and B, these are real numbers, right? And in order for this to be a solution to the Einstein-scalar field equations, they have to satisfy these relations, right? Okay, so this is an example of a solution. And now we can apply this recipe. So for any constant t here, strictly larger than 0, we can look at the induced initial data, and we can do this expansion normalization, apply this to these initial data. And what we get then is that the script k bar is an operator whose eigenvalues are exactly the pi's. These are the eigenvalues of this script k bar. And the eigenvectors are the d by dxi. The script h bar is just the flat Euclidean metric on the d torus, or n torus. And then, well, the phi 1 bar and phi 0 bar are the A and B, right? So in this case, if you do this expansion normalization, the expansion normalized data are independent of t. In this particular case, it doesn't even depend on t at all. So clearly the limit exists, right? And you get data on the singularity. So here nothing happens at all, right? Okay, so this almost finishes the introduction. Let's see. So to finish now the introduction, let me mention some results, previous results. So there are lots of results in situations with symmetry, and these I find very interesting because, I mean, in symmetric situations, you can perhaps prove results for large initial data and so on and so forth. You can prove perhaps for results for generic solutions in that symmetry class. So that's very nice, but I'm not going to say anything about that. There are also actually lots of nice and important numerical results which have inspired the mathematical analysis. I'm actually not going to say anything about that either. So the results I've listed here, they're only results, so mathematical results in the absence of symmetries, right? So the first result I'm going to mention here is by Lars Andersson and Alan Rendell. So they put data on the singularity for the Einstein-scalar field equations or for the Einstein-stiff fluid equations in the real analytic setting and then proved that there are corresponding solutions. So this is a result from 2001. This was generalized by Thibaut Damour et al. To higher dimensions. Then there are, I mean, these results in some sense are perhaps not so relevant for this talk, but I find them very important, so I wrote them down anyway. So Paul Klinger, who was here in Vienna, incidentally, and Greg Fournodavlos and Jonathan Luke, they have interesting results in the vacuum setting. So putting data on the singularity in the 3+1 dimensional vacuum setting. So from what I told you, that shouldn't be possible. But if you kill off an extra function, you can actually do that, right? So you have to remove some degree of freedom in order for that to be possible. But you can do it in the absence of symmetries. Then in recent years, there have been quite a lot of results on stable Big Bang formation. It sort of started with the work of Igor Rodnianski and Speck in 2018. So they're studying the stability of spatially homogeneous and isotropic solutions, which are also spatially flat, right? And then they're proving that these solutions, the Einstein-scalar field equations, that they're stable. I think also it might be that they consider stiff fluid equations as well. I don't remember. But so this is the result of Igor and Jared, the first one. And then Jared considered the case of S3 spatial topology, so spatially homogeneous and isotropic, but with spherical geometry. And then Florian Bayer and Todd Olenek, they proved a result in a similar setting as the original result by Igor and Jared, but they used a different gauge, which you can localize. And this is quite interesting to sort of localize the analysis. David Feynman and Liam Urban, they have an important result then concerning the hyperbolic settings. They have hyperbolic geometry, and they also prove future global nonlinear stability in this setting. Right? And Florian and Todd, they generalized their results to include a fluid. This Liam was mentioning on Tuesday, and then you have the results by David and Liam, which was you heard about on Tuesday. Right? Okay, but this is sort of close to isotropy. Then there is a result which is sort of like intermediate anisotropy, so you allow a little bit of anisotropy, but not the full range that you would like to be able to analyze. And then, I mean, the most important result sort of for this talk is the result by Gregorius Fournodavlos, Igor Rodnianski, and Speck, right? So they proved stability, actually they proved stability of this solution. I mean, they proved some other things also, but the main point is they proved stability of this solution, assuming the PI satisfied this condition we expect to be necessary to get quiescent behavior, right? So that's contained there. But so it's an important result from that point of view, but it's also important because there's significant overlap. Their methods also inspired us in our work. Okay, so so now I'm finished with the introduction. So now I have 13 minutes or so for the talk. So, okay, so now I'm gonna describe the result, right? Okay, so what is the result here? So I'm interested in the Einstein nonlinear scalar field equations. So I have a potential, and I have to make some assumptions concerning the potential in order to get a result. And okay, so the potential is going to be smooth. I'm going to assume that it's non-negative. You could get around that. The main assumption is really that it cannot grow too quickly, right? So it can grow exponentially, but I don't want it to grow faster than e raised to 2 absolute value x, because then I have problems. Strictly speaking, this 2 should be replaced by dimensionally dependent constant, but this dimensionally dependent constant converges to 2 as n goes to infinity. So if I want to have the same number here, I put 2, right? So I don't really want to be on the borderline here. I really want to have a margin away from 2 e raised to 2 absolute value x, and that's what this little parameter sigma v, the point of the sigma v is that it's a margin to bad potentials, right? So that's the only thing you need to recall from this part. Then I'm going to restrict my attention to constant mean curvature initial data. And I'm going to assume that the mean curvature is strictly positive and that the associated expansion normalized data are such that this condition on the eigenvalues is satisfied, right? So as I told you earlier, this is expected to be a necessary condition on the eigenvalues. So I need this to be positive, and I want a little margin. So sigma p is some positive number here, which I'm insisting that this be positive. Okay. Here I will assume actually that I have non-degeneracy. We need this for our methods. I don't expect this to be necessary, and sometimes we can avoid this condition. So I'm going to assume sigma to be a closed manifold, and I'm also going to assume it to be parallelizable. If I assume non-degeneracy, that's not really an issue, because if you have non-degeneracy, there will be a finite covering space of sigma, which will be closed and parallelizable. So it's actually not, from that point of view, it's not an issue. If you're interested in 3+1 dimensions, well, all closed and oriented 3 manifolds are parallelizable, right? So that's not a condition in that case either, right? So that's not really much of a condition. Next condition is slightly technical. So I'm going to impose bounds on Sobolev norms of the expansion normalized data. And so I need to tell you what the Sobolev exponents are. And this is slightly technical. It's not extremely important, the details here. But first you fix a k0, and the lower bound sort of only depends on the spatial dimension, which is n. And then I have a k1, which has a lower bound. And the interesting thing here is I divide by sigma. So sigma is this object. So you remember, as sigma v goes to 0, then you get close to the potentials you can deal with. As sigma p goes to 0, you get to the boundary to the type of eigenvalues you can deal with, right? So as this goes to 0, the number of derivatives you need to control blows up, right, in this argument. Okay, so now comes actually the statement and the conclusions. Okay, so bear with me here for a little bit. So the statement is the following. If you give me a constant theta 0, and you should think of theta 0 as being a very big constant. You give me this constant. What I will give you in return is another big constant, theta 1. So that if these expansion normalized data are bounded by theta 0, and you have this non-degeneracy bound, and if the mean curvature is initially bounded from below by theta 1, then the maximal goal by hyperbolic development will have a Big Bang singularity with curvature blowup. Okay, so this is a slightly technical condition. So let's contemplate this condition for a moment. right? So in order to get some feeling for this condition, it's useful to think of this a solution that induces data on the singularity. So let's assume that we have a solution inducing data on the singularity. Well, in that situation, you will, in the limit, so the limits of this expression will be strictly positive. So this will be satisfied sort of uniformly, in some neighborhood of the singularity, will be satisfied in some neighborhood of the singularity. And this will, if the eigenvalues are distinct on the singularity, this is also going to be satisfied in the neighborhood of the singularity. And also, these objects you expect, H bar inverse, H bar, K bar, all these objects are supposed to converge in the direction of the singularity. So these things will all be uniformly bounded in the direction of the singularity. So you expect all these things to be uniformly bounded as the mean curvature blows up, right? So for that reason, it's quite natural to first impose a bound on this, and then you turn up the mean curvature. Every solution that induces data on the singularity will be such that this is uniformly bounded as the mean curvature blows up, right? So this condition will be satisfied by every solution that induces data on the singularity. Right? But on the other hand, and this I want to emphasize now, all the results I mentioned previously were stability results. You started with a specific solution, you asked yourself the question, is the solution stable in the direction of the singularity? This condition does not refer to any background solution whatsoever. There is no background solution in this condition at all, right? This is a general condition on the initial data without any reference to any background solution. So in that sense, it's not a stability result, right? Okay, so if you assume now that these conditions are satisfied, what are the conclusions you get? So first, the past of the initial hypersurface is foliated by constant mean curvature hypersurfaces and ranging all the way up to infinity. So the mean curvature is going to range all the way up to infinity. So you have a crushing singularity and the mean curvature is sort of blowing up, right? Okay, so that's the first conclusion. If you look at the eigenvalues of the expansion normalized Weingart map on the leaves of the CMC foliation, they're going to converge to limits. So there will be this LA ring, which will be the limits. Okay. If you look at these expansion normalized versions of the scalar field, they are going to converge also to limits here. You will get this, well, the Kastner relation will be satisfied, and you will get this asymptotic version of the Hamiltonian constraint will be satisfied. This sort of necessary condition on the eigenvalues will be satisfied in the limit, as you expect. But also, you will get curvature blowup, right? So if phi1 ring is non-zero, this space-time Ricci curvature contracted with itself is going to blow up in the direction of the singularity. But irrespective of whether phi1 ring is zero or not, the space-time Riemann curvature contracted with itself is going to blow up in the direction of the singularity. And finally, all causal geodesics are going to be incomplete to the past. Okay, so I should point out here that we are in a situation where actually Hawking's theorem need not apply. So we can't get this conclusion from Hawking's theorem, so we have to prove it separately. But anyway, all causal geodesics are incomplete to the past in this setting. Okay, so I'm progressing a bit more quickly than I thought. So I have some time. Okay, anyway, so let me perhaps make some remarks, extremely brief remarks concerning the proof. So the main problem we have is, of course, that we don't have a background solution that we're proving the stability of. We don't have a background solution, and that's sort of a problem. But it turns out we can construct a substitute for this background solution, and we call this substitute then the scaffold. So we use the initial data to construct this scaffold, which is effectively a substitute for background solution. And then in the end, you prove a bootstrap argument showing that in some suitable sense, you don't stray away too far from the scaffold somehow. This is sort of the very, very roughly the argument. And as I mentioned, in the conditions, I required non-degeneracy, that the eigenvalues are distinct. And I need this non-degeneracy in order to construct the scaffold. But if you actually have a background solution, you can use this background solution as a scaffold, and then you don't actually need this non-degeneracy. So if you have a background solution, then you can sort of use the argument to prove sort of stability of that background solution also, right? So it's worth comparing then. So if you look at this result by Greg, Igor, and Jared, so the stability of these solutions, so this follows as a special case of this result. And if you take Jared, Speck, I mean, I should say actually, so I divided it. Were results about in the isotropic setting, the near isotropic setting, and the general setting. And actually, the results in the isotropic setting have somewhat better asymptotics. So it's not quite interchangeable, these things, right? But so anyway, so Jared Speck, he proved that if you take the three-sphere, you take an isotropic solution, a spatially homogeneous and isotropic solution with initial data on the three-sphere, right? So that's going to have a big bang, then maximal expansion, then a big crunch, right? And he proved that in the Einstein-scalar field setting, this is stable. I mean, both to the future and to the past. But I mean, one corollary of our result is that if you take any left invariant initial data for the Einstein-scalar field equations on SU2, so take any left invariant initial data to the Einstein-scalar field equations on SU2, so that's Bianchi 9 for those in the relativity community. So if you take any such data, you're going to have a big bang, maximal expansion, and big crunch. And all of those are stable, both to the future and the past. This is, again, a corollary of our result, not only the isotropic one, right? And it's sort of worth mentioning that those solutions could have this feature that you bounce around close to this chaotic dynamics for as long as you wish, right? But anyway, these solutions are also stable both to the future and the past. Then you have the result by David and Liam. So this was in the hyperbolic setting. This also follows from our result, but again, not quite as detailed asymptotics actually. And also they prove future global nonlinear stability in the Einstein-scalar field equations. We don't get that, but we do get future global nonlinear stability for appropriate potential somehow. Okay, and then, as I said, I mean, if you have a solution which induces data on the singularity, well, then, I mean, the assumptions of the theorem are constructed so that those will be stable, right? So if you have any solution that induces data on the singularity, well, that solution will be stable, right? That's going to follow directly from the setup. Right? And then, I mean, there are large classes of spatially, locally homogeneous solutions that are globally nonlinearly stable, so both to the past and to the future. And this sort of, again, follows from the fact that in the Einstein nonlinear scalar field setting, there are plenty of stability results to the future, and you can combine them with these results to get, all the way from the Big Bang all the way to the future, and this follows as a corollary. Okay, there are lots of things to be done. We do get the conclusion that the curvature blows up in the direction of the singularity, but we don't get as much information in the direction of the singularity as we would like. We would like to prove that these solutions actually induce data on the singularity, but our results are not at all strong enough to do that, and it's quite conceivable that the methods are inappropriate even for that, right? So I mean, there's a reason why you can get these results in this general setting, and that is that you can actually close bootstrap assumptions which are not very strong. I mean, you can surprisingly, close a bootstrap argument where the bootstrap assumptions are not very strong, but then of course since the bootstrap assumptions are not very strong, it's easier to close the bootstrap argument, but since they're not very strong, you don't get so much information, right? So this is sort of, so there's work to be done. You really would like to get data on the singularity. And then, I mean, all of this is done in the CMC setting, so CMC foliations, and it's very nice to look at this constant mean curvature foliation, because this will sort of automatically synchronize the singularity, so it occurs as t equals 0, so to speak, everywhere. Otherwise, I mean, there's no reason to expect that. But somehow, if you want to look at more complicated cosmological models, you might want to localize in space the analysis somehow. And then these CMC foliations, it's not so clear that that's a useful methods for that. And with that, I thank you for your attention.